In this video, we're going to go over the factoring quiz that I'm asking you all to complete in class today. My original plan was to be here in person and to help each of you go through the quiz and go over the different techniques, perhaps even do so in small groups. But since I'm not there, then this video will have to suffice. So first thing that I want to do is real quickly revisit the factoring techniques that we've seen so far, and then we'll see how they're applied with a particular quiz. Now, I've got a printed copy of the quiz that we're completing here, and I'm not 100% sure if the quiz questions that you see will be done in the same order. I believe the setting is to maintain order and then randomize the choices. But in the event that your questions are a little bit out of order, my goal is to go through all of these solution sets and get you to the correct answers for each one. So I'd like to see a perfect score for everybody on this particular quiz. Now, the first factoring technique that we learned about last week and practiced yesterday in class was GCF, which stands for greatest common factor. And the greatest common factor is our way of just simply reducing the size of the coefficients and perhaps the variables themselves with each term in the polynomial. As long as every term in the polynomial has an element that can be factored out, then that's the technique that we would use to factor. Now, a lot of times a GCF can take a standard trinomial where a is not equal to 1 and end up reducing it back to a standard trinomial where a is equal to 1. And we noted that when standard trinomials have a leading coefficient of 1, then we just simply looked for factors of c, the last number in our polynomial, that add or subtract to make b the coefficient in the middle. So they add or subtract to make b. Those were the nice trinomials. While it may be a little bit tedious to find factors sometimes, at least we only had to worry about one factor pair. And the one factor pair that added or subtracted to make the term b, or the coefficient b in the center, that was the pair that ended up working. Now, standard trinomials with a not equal to 1, I use this symbol here when I'm typing not equal to. We see that in some coding languages. But this little phrase here means that a is not equal to 1. In this case, we had to find factors of a and c, so factors of the beginning and the trailing coefficients. And the factors of a and c, you have to choose those carefully so that they FOIL. They don't just necessarily add or subtract, but they have to FOIL together to make b. So this one was a little bit more complicated. Now, I didn't teach this in class, but there are other techniques to help with this. If you search online for the X method, or if you use something called split the middle, there are plenty of videos online that help explain these techniques. These are alternatives to the guess and check that I've been teaching in class. In fact, I think on my channel I do have an older video on split the middle if you'd like to look at that and see some of those examples as well. Now, for standard trinomials that are not equal to 1, I prefer the guess and check method. That's what I just described here. But with any luck, there's a GCF that reduces our problem into a standard trinomial with a equal to 1, and we can proceed from there. Now, the difference of two squares, we saw this on occasion. That's where we only have two terms. Both have square roots. That's what we mean by square numbers. Both have square roots. And finally, there's a subtraction sign in between. And if all of those criteria are met, then we can use the shortcut here. And that's where we take the square root of both terms and create two binomials, one with a positive and one with a negative. I'll show you that when we get to that at the end. Finally, the factor by grouping technique. This is good for a polynomial that has 4 terms. And this is where we take the GCF of the first two and then a GCF of the last two. And if they match, if a common term exists, we'll say, if a common term exists, then we proceed with the final answer. If a common term doesn't exist, then we can't proceed with the final answer, and we'd have to abandon that and use another technique to try to factor. So in both of these cases, I didn't really explain the solutions here, but you'll see them as an example as we move forward in this quiz. So here we go. In question number 1, we're being asked to factor the quadratic expression completely. There's a clue that we're trying to factor completely. And the first thing that I always check for is a GCF. In this case, there is a GCF. There's a 6, an 8, and a 14 that's acting, or that are our coefficients, A, B, and C. And so to me, it looks like all three of those can be divided by 2. So because of that, I'm going to factor out a 2, and I'm going to see what's left over. What's left behind is a 3x squared, a 4x, and a 7. So I think I got the entire GCF because I don't notice anything that's left behind that's still factorable. And so since there's nothing else that's left behind that's factorable, I know that 2 is our GCF, and it's our only GCF here. Now if I look at my answer choices, and my job was to factor completely, well, there's only one answer choice that contains the leading coefficient of 2. So that leads me to believe that this is a good answer. Now, we may, on occasion, be able to continue to factor further into 2 binomial groups, like suggested here with part A and part D. But in order for that to be possible, we'd have to be able to find 2 factors of 3 and 2 factors of 7 that FOIL together to make 4. So I'm going to go ahead and write 2 here out front. I'm going to assume that this is factorable. Let's just check this out. I know that 3x times x will multiply to make x squared. And I also know that 7 times 1 will multiply to make 7. But if I go through the FOILing process here, the outside product for those two turns into 21x, and the inside product turns into 1x. As far as the FOILing process goes, these two cannot return or FOIL back together to make 4. So that combination is no good. But I'm not done yet. I should check all combinations. And so I'm going to look at the other combination. What if I put a 7 here and a 1 here? Well, now I'm tempted. Now I see that I have a 3x times 1. That makes 3x. And a 7 times x makes 7x. I could use a 7x and a 3x to get back to 4. But in order to make that happen, I would have needed a positive 7 and a negative 3. To make a positive 7x and a negative 3x in the green ink, that means that this 3x would have to have multiplied by negative 1, and this 7x would have had to have been positive here. Positive 7 times positive x equals 7x. And at first glance that looks pretty good, but then we have to realize too that the numbers that we chose here, 7 and 1, have to multiply to make this 7. Not just numerically, but with the signs as well. So positive 7 times negative 1 does not equal positive 7. So as it turns out, this is not the correct factoring method. It looks good, but it's not quite right, so we can't go with it. All of that to say, the solution that we found back here, before I started marking it up with this green ink, that was the correct answer altogether. So the solution that we thought we had was indeed the correct one after all. Let's move on to number 2. So in question 2, just like we saw before, the first step that I would go through is to find a GCF. Now I noticed that all 3 of these terms could be divided by the number 3, but they could also be divided by the letter x. Each one had at least one x to give up. So after the GCF step, I see that 3x is reported out front, and we've got this trinomial that's left over. I didn't mention it in the last example, but my goal after the second one would be to factor the trinomial, and we would use the techniques that are necessary. In this case, we know that a is not equal to 1, so we'd have to use the process to factor a trinomial where a is not equal to 1. And if it was possible to do so, we would. But I think we run into the same problem on this example as we did on the last one. I'm trying to use color coding here so that you can see the connections, but since this is a standard trinomial with a not equal to 1, I'm looking for two factors that multiply to make 2x squared. Well, I've settled on 2x and x, those that are highlighted in blue. I'm looking for two numbers that multiply to make 3. I've included them in yellow here, 1 and 3. And in this orientation, it looks like we might be able to FOIL back together to make 5. I think we've got a 2x times 3, which makes 6x on the outside, a 1 times x on the inside. Well, if I had a positive 6x take away 1x, that would have gotten me back to 5. But unfortunately, in our final check here, this negative 1 should be multiplied by positive 3 to finish the foiling process, and negative 1 times positive 3 does not equal negative 3. I'm sorry, it does not equal positive 3. It equals negative 3. And so we were trying to get back to this statement here, this value at the top, and our foiling process didn't leave us there. So even though it was tempting to say that that was the solution, it was not. As it turns out, the only solution for this particular set, again, is this option here, with the GCF out front and a trinomial that remains at the bottom. So now moving on to question 3. This is one of those special formats. This term up front and this term in the back, there are only two of them. They both have square roots. Moreover, they have a square root and they're separated by a subtraction sign. So this perfectly follows our difference of two squares pattern. So since this follows a difference of two squares, we can jump straight to the solution without showing any math. The solution requires the square root of the first term, reported here at the beginning, the square root of the second term, reported in the second positions of each of these binomials. And in order to obtain the minus sign in the middle, we need a positive number to be multiplied by a negative number. Now, if you recall, this works out nicely because in the foiling process, especially when we get to the outside products, in this case negative 4, and the inside products, positive 4, 4x that is, when we add them together because they're like terms, they end up canceling out and disappearing. You'll notice that in the original problem here, there was no middle term, only the negative sign. So without the middle term, that meant that our outside and inside products canceled one another. And here's our final solution in order to make that happen. X plus 4, x minus 4. Now I've noticed that all three of these answers so far have been answer choice number 2. Let's see if that continues. And that may or may not be the case for your quiz set too. Here's another example of difference of two squares. This first term has a square root. The second term has a square root. They're separated by a subtraction sign, so we can jump straight to the solution here, again, because this follows the difference of two squares format. The square root of 4x squared is 2x. The square root of 81 is 9. One group has to have a positive sign. One group has to have a negative sign in order for the foiling to work. And we know that 2x plus 9, 2x minus 9 is a good final answer. And what do you know? It's option 2. Question 5. Completely factor this quadratic expression. Now, it's not a difference of two squares. We don't have a GCF, I don't see, so I bet this is a standard trinomial with a equal to 1. So when factoring a standard trinomial with a equal to 1, remember a being the number that's in front of the x squared, when a is equal to 1, we just need to find factors of c, the last number in the group, that add or subtract to equal the number in the middle. Well, that should be pretty easy to do. The beginning always starts with x times x. That's what's going to get us back to the x squared. The two numbers that multiply to make 14, that add or subtract to make 9, well, if you don't see it immediately, remember we can create a full list of our factors, the largest and the smallest, and then work our way back to the middle. But I think that's it for this group. There's no number between 2 and 7 that goes into 4, but that's okay because 2 and 7 I think are the choices that we want. A positive 2 times a positive 7 multiplies to make 14, but also a positive 2 plus 7 equals 9. And wouldn't you know it, answer option 2 is the result here. Question 6. Here we have another standard trinomial. We have everything written in descending order by exponents. We have an x squared, an x to the first, and in theory we've got an x to the 0 power here. That's exactly what we've got. Leading coefficient is 1, so we should be able to jump to the factored form pretty quickly. x and x will be used to start the problem. Two numbers that multiply to make 18 that add or subtract to equal 3. Well, I like the number -6 and +3. Again, -6 times +3 multiplies to make 18. -6 plus 3 adds to equal -3x. So x plus 3 and x minus 6, there you are, answer choice number 2. Now, we do have an answer that's out of order, but we had mentioned this in class before. Multiplication's commutative, so it doesn't really matter the order that you write them in. They both mean the same thing. Both of these factors are the correct ones for this particular example. So again, real quick to remind ourselves, we had a -6 times 3 that equaled 18, but -6 plus 3 that added to make the +3 in the center. I'm sorry, the -3 in the center. Let's see what we get for the other examples. Here's another standard trinomial with a equal to 1. So let's see if we can figure this guy out. X and x must start our binomial pairs, and we're looking for two numbers that multiply together to make 70, that add or subtract to equal 3. I had mentioned in class before that the numbers that we choose, the factors that we choose, are often close to one another in the list of factors. So if I've got the number 70 and I'm trying to think of all of the factor pairs because they're hard to come up with, I might start with 1 and 70, might jump to 2 and 35 and keep working my way through. And the remaining factors are 5 and 14 and then 7 and 10. Now again, I had mentioned in class, it's often these factor pairs that are in the middle, maybe the 7 and the 10 or the 5 and the 14. Those a lot of times end up making the middle term that we're going after. Any one of these pairs will multiply together to make the 70. That's why we chose them, but only one pair will add or subtract to equal +3. And hopefully you figured it out. If we had a 10 and a 7, those are only 3 units apart. So that's the pair that we want to use. And I think a +10 take away 7. So +10 minus 7. That's what's going to get us back to +3. And also +10 times -7. That's what multiplies to make the -70. So I'm happy with this as an answer, and as far as an answer choice goes, wouldn't you know it, option B, x minus 7 and x plus 10. Let's go out on a limb here and make our guess. Is the second choice the best answer? Well, that's been the pattern so far, but let's see if we're right. Remember, in any case, you can always check your answer by foiling the results back together. So we're guessing that x minus 8 and x minus 2 are the factor pairs. What's going to happen if we foil them together? First off, we have x times x. That makes x squared. Secondly, we have x times -2. That's -2x. Thirdly, -8 times x is -8x. And then finally, -8 times -8 times -2 makes a +16. Now that doesn't look like the original right now, but if you recall, we can and should combine like terms. The x squared and the +16 have nothing to combine with, but the -2x and the -8x, those do combine to make -10x. This result after foiling does match what we had started with, so that means I'm pretty happy with this as an answer, x minus 8 and x minus 2. Okay, so now we get to the last two of the quiz, and I think these are the most difficult of the examples we've seen so far. We have a standard trinomial, 3 terms. Each term, whoops, there's a bit of a typo here. I think this is supposed to be an x. Let's go ahead and assume that that's an x. Each term has the same variable with a decreasing exponent, so x squared, x, and then technically this would have been x to the 0 power. So that's good so far, but one thing that we don't have is a common factor. There's no number that goes into 3, 22, and 7. There may be some common factors amongst 2 of the terms, but in order for us to use the GCF method, they have to be common to all 3. So here's where we need to guess and check. Again, we will go ahead and set up our parenthesis groups. And we're looking for 2 numbers that multiply to make 3, or in this case 3x. Now 3 is a prime number, so we don't have a whole lot to choose from. 3x times x is the only option we've got. And we could technically switch these around and and use x and 3x. That's okay, but I'm not going to do that unless I absolutely have to. We can also do the same thing here with the 7 at the end. 2 numbers that multiply to make 7. There's only 2 of them, a 1 and a 7. So that's our guess. Now comes our check. In our check, we're foiling things together. We're looking at the outside products, that's a 21x, and the inside products, which are 1x. Can 21x and 1x combine to make 22x? Well, they certainly could if both were positive. Now, if both were positive, in order to get this 21x from this outside group, this positive 3x would have to multiply by a positive 7. This positive x would have to multiply by a positive 1. And I think a 3x plus 1 and an x plus 7 end up being the pair that works. Let's finish this out. Last one. We have a prime number in front, which is helpful. I know that 5x will have to multiply by x in this standard trinomial. We have some choices, though, for the number 18. Now, with 18, we can use 1 and 18. We can choose 2 and 9. We can choose 3 and 6, and any combination of those would work. So as I said before, the two numbers that are closest to one another tend to be the answers a significant or surprising amount of the time. So I'm going to start with 6 and 3. Now I might guess that I'm going to put a 6 here and a 3 here, and that's a fine guess, but when we check this, we're going to notice that something's off. 5x times 3 ends up being 15x. 6 times x is 6x. Can 15x and 6x combine or add or subtract to equal 33? The answer is no. But I don't want to give up on the 6 and the 3 just yet, because I can switch the order and I might get a result that I'm after. So what if I put the 3 here and a 6 here? Well, now in the act of foiling to check, the outside product becomes 30x, the inside product becomes 3x, and now if I had a positive 30 and a positive 3, then I'd be able to get back to this 33x that we were after. So this positive 6 times this positive 5 made the 30x. This positive x times a positive 3 would make 3x, and I'm happy with this answer group, 5x plus 3 and x plus 6. Oh, I thought we were done. How many questions are on here? Well, those are the answer sheet. Okay, so we got to get to problem 12. Sorry about that. I thought we were done at 10. Let's go ahead and wrap these up real quick. This looks like a standard, and this one looks like a standard, so guessing and checking is going to be the way to go. I'm going to go ahead and pause the video and finish these, and you can pause it as well. Try them on your own, and resume playback in a moment to check your work. I wonder if we can go for a perfect score here. Are those two going to be the answer? Let's see. Okay, so I think our streak has been preserved. I do agree with both of those answer choices, and let me show you how I got there. In the first example, I knew that I had to pick two numbers that multiplied to make 6 and two numbers that multiplied to make 7. That's part of our standard trinomial process when a is not equal to 1. So I guessed 6x and x and then 1 and 7 in these positions, but I crossed that out because in the foiling process, 6x times 7 is 42x and 1x. Those were way too far apart. They couldn't have combined to make the 1x. So by switching around the 7 and the 1, 6x times x is still 6x squared. 7 times 1 is still 7x, but more importantly, on the outside products, I end up with 6x. So 6 times 1 is 6. And on the inside product, 7 times 1x is 7x. And the positive 7x take away 6x would have gotten me back to a positive 1x. And so I like 6x plus 7 and x minus 1 as my factors. And in the final example, I knew I needed to pick two numbers that multiplied together to make 20. So I started off with 20 and 1, and two numbers that multiplied to make 12. So I started off with 1 and 12. And then I remembered that these are way too far apart. I knew that this 20 times 12, which is way I didn't even do the math on that one, actually. It was way too big and 1x. There's no way I could have added those back together to equal 1x. And then I remembered, well, pick two numbers that are close to one another and use them as our factor groups. So I chose 5 times 4 to make 20. That worked. And then I chose 3 times 4 to make 12. And that worked. But in the foiling process, 5 times 4 gave me 20x. 3 times 4 gave me 12x, and there was no way for 12x and 20x to combine to make 1x. I didn't give up on that combination, however, so I switched to the 3 and the 4. Now 5 times 4 still gives me 20. 4 times 3 still gives me 12. And now in the act of foiling, the outside products produce 15x. The inside products produce 16x. And a positive 16, take away 15, is what led me to the positive 1x in the center. So I was happy with 5x plus 4 and 4x minus 3 as the solution, albeit slightly out of order. So there you have it, the quiz, questions 1 through 12, covering pretty much all the factoring techniques we've covered in class so far. The only ones we haven't seen now are the factor by grouping. We'll spend some more time on that tomorrow. Thanks for watching.